Some neural nets are broken before training starts. Xavier and He initialization set the weights so signals can actually flow. This is the pattern you'll be able to implement by the end, which weighs layer gradients and chooses the steadier starting weights. I'm Professor Pi, teaching AI foundations with simple Python. Weight initialization fixes a very practical failure mode. If the first weights are too large, activations blow up. If they're too small, signals vanish. Either way, gradients suffer and training stalls. That's why practitioners use Xavier and He. They're simple, layer-aware scales that keep signals behaving for common activations. The intuition is straightforward. You want each layer to forward roughly the same variance. Xavier balances fan-in and fan-out, which fits symmetric squashing functions like tan. He leans on fan-in, which matches rectifiers that drop half the inputs. We'll build tiny PyTorch examples. First a naive oversized init, then Xavier and He applied step by step. You'll watch activation spreads, gradient norms, and one optimization step, so the behavior is concrete. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, I want to show the problem directly by creating a toy input and a naive, large weight matrix. This snippet shows how oversized initial weights blow up activations. I create a small, easy-to-read input tensor X and a weight matrix W scaled aggressively 5 times. Then compute Y equals X at W so you can see the effect. I call y.std unbiased equals false to report the population spread. And that printed number makes it obvious why careless initialization destabilizes training. Now that we can measure an explosion, we calm the layer for a TANAC activation using Xavier scaling. This example sets up a PyTorch linear layer and applies Xavier-style scaling tuned for tang. I'll compute the gain with calculate gain, combine fan-in and fan-out into the matching scale, and use a simple alternating sine pattern tensor as the base. Inside torch.nn, I copy the scaled values into layer.weight and leave bias at 0, so the start is symmetric. I keep a small target tensor for later, pass X through the layer, then apply torch.tang and inspect the standard deviation to confirm the activations are tempered. Seeing activations look reasonable is good, but we must check gradients. F.relu behaves differently, so we compare gradient magnitudes under 2 scalings. This code defines a helper grad for that measures how initialization affects gradient norms under a F.relu loss. Each call spawns a fresh linear, copies the shared sine pattern scaled either by 5.0 or 1.0, runs the forward pass, applies F.relu, and computes mean squared error against the stored target. Because each call builds its own graph, returning the Frobenius norm of model.weight.grad oscillates the gradient magnitude for that scaling. Calling grad4 twice captures the naive oversized case and the He scaled baseline, and printing their ratio shows how much steadier the He initialization makes learning. Next, we combine the 2 ideas and test a small stack where the first layer suits tanh and the second suits F.relu to see how variance flows through depth. This snippet builds a 2-layer nn.sequential that mixes Xavier and He across the activations. At index 0, I copy the pattern multiplied by the Xavier scale, so the tan-half friendly first layer starts centered. And at index 1, I apply the He-style unit scale right before the F.relu. Using torch.nograd while copying keeps gradients clean and ensures each module begins with the intended matrix. Running the network on X pushes data through tanh then F.relu, and inspecting the final F.relu standard deviation shows the mixed initialization still controls variance through through a small depth. Finally, we show that a single optimization step on a He initialized ReLU layer actually behaves calmly and reduces loss. This example runs one SGD step on the He initialized ReLU layer to demonstrate stable optimization. After copying the balanced pattern into model.weight, I attach an optimizer with LR equals 0.1, compute predictions equals F.relu model X, and use MSE against the stored target. Backward computes gradients similar to those measured earlier. Optimizer step nudges the weights without explosion thanks to the normalized scale. And recomputing the predictions plus the new MSE shows the single update reduced loss and behaved calmly. Mapping this toy example to a real project is straightforward. For a small image classifier, the same He rule stabilizes convolutional layers with ReLU. For a regression model that uses tan outputs, Xavier keeps gradients centered so training proceeds more smoothly. To recap briefly, these are compact formulas that pick initial weight variance from layer size and activation. Use Xavier when your layer uses a symmetric squashing function like tang, and use He when you're using ReLU-style rectifiers. One caveat, these rules help a lot, but you still need sensible learning rates and batch sizes for robust training. Next step, run a short learning rate sweep on your He initialized ReLU network to find the largest stable learning rate and see speed improvements. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.